So we are going to start our next section, section 7, liquefaction analysis in FLAC. So liquefaction analysis is a type of the dynamic analysis procedure that we also consider flow and pore water pressure inside the soil during the earthquake excitation. At the beginning of this chapter, we are going to provide a short introduction of the liquefaction phenomenon. And then after that, we are going to discuss the formulation of liquefaction that FLAC uses for its primary liquefaction model. And we are going to introduce the constitutive model for the liquefaction analysis. And then we will also do an example using an example of a dynamic analysis of an embankment dam, and performing a liquefaction analysis on that and determining the liquefaction potential of the cohesionless sand layers that are saturated with water. So this example also includes a flow analysis as well, because before we perform the liquefaction analysis on this embankment dam, we are going to rise the reservoir water in the embankment dam, perform a flow analysis, and analyzing this system so we can get the steadiest safe flow inside the embankment dam. And then after that, we are going to perform a dynamic analysis for our system. So therefore, we are going to start from the introduction to liquefaction. So liquefaction is the frequent cause of failure during earthquakes, specifically on areas that they are close to water, the seaside, the wharf, and then the quay walls. For instance, quay walls are the retaining walls that are built adjacent to the ports. So the major investigations with regard to the liquefaction have been initiated in 1960s, specifically after two major earthquakes. One of them was 1964 Niigata earthquake in Japan, and then 1964 Alaska earthquake. And then after these two events, major catastrophes were seen as a result of liquefaction, and therefore after that significant studies and research have been done with regard to the liquefaction topic. We see that in liquefaction phenomenon that in many cases the structures remain intact, and we don't see any structural failure in the system. The phenomenon that is seen during the liquefaction is removing or eliminating the soil support, and therefore the whole structure starts flipping, and therefore we don't see any structural failure. We see just eliminating the support of the structure. And this is the famous figure and photo of the liquefaction event that was happened in 1964 Niigata earthquake, and a lot of these big complex buildings were flipped due to the loss of their supports at the soil layer. Some other areas, sometimes we also see the whole structure is sinked in the ground because of the loss of support there. And therefore, we are going to just do a quick review of the mechanism of liquefaction and how it happens. And then based on that, we are going to continue with regard to the formulation of liquefaction in soil layers. Okay. So we'll start from the loose sand in the drained conditions. So let's say we have a sample of sand layers that is under shear force, and then the sand layer is in a loose condition. And then once we are applying a shear force, because our layer is in a drained mode, so that means that the shear force is applied gradually. So in that condition, so the gradual loading, which is mostly happened in the static loading, because the sand has a very high permeability. So during that gradual loading, we'll see the water dissipation in the sand, and then the soil starts to get deformation, and that deformation changes the porosity between the particles, and therefore water will escape from the elements and the particles, and then the pore water pressure releases and escapes. So eventually the soil will be more compact, and then the water will be drained from the soil, and then we don't see any excess pore water pressure in the system. In the other word, the pore water pressure escapes and is released. So that is the mechanism of a sand layer under shear forces in the drained condition. So once we get to an earthquake loading, the drain condition of the loading is going to be switched to an undrained condition. So in the earthquake loading, for the same sample of the sand, which is a loose sand under shear force, this time we have the earthquake shear force, which is actually a cyclic loading. And because the cyclic shear force is applied in a very small amount of time, in just 1/10 of seconds or lower or close to that number. So in that case, the water will not have enough time to get dissipated from the soil particles. And therefore, an undrained condition will happen for a very short time, in a temporary time during the earthquake event. So in that case, during the earthquake event, we are going to see an undrained condition. So in that case, because of the time is very short and the cycling shear stresses are applying to the soil, so we see that the water cannot actually dissipate through the soil particles and cannot drain through the soil particle. In the other word, we see that water imprisoned in soil particle. And then also in the other word, we see that pore water pressure that actually in the static case, it could escape and release. This time it cannot escape and release from the soil particle. So in that case, we are seeing an increase of the pore water pressure. So the pore water pressure inside the soil particles will be increased. So what will happen once the pore water pressure is increased during an earthquake event because of the imprisoning of the water particles inside the soil particles? The event that is going to be happen is it follows the stress state in the soil layers. So we see that based on the basic fundamental soil mechanics equation, we know that at any layer of a system, the total stress that is applied to that specific layer of the system is equal to the summation of the effective stress and pore water pressure. Effective stress is the stress between the particle, and pore water pressure is the pressure in the water content inside the void. So therefore, the total stress is equal to effective stress plus the pore water pressure. So once we also know that the total stress is actually a constant value. So in that case, once we are having the increase of the pore water pressure, once we have the increase of the pore water pressure due to the imprisoning of the water particle inside the soil particles, in that case, because the total stress is going to be constant, so therefore the pressure between the soil particles is starting to being decreased, and then therefore the effective stress decreases during this event, and this decrease can get more significant, and sometimes we get it reaches zero. So zero effective stress means that we do not have any contact between soil particles. We are not having any stress applied to the soil particle, and therefore the soil particle will be basically as a buoyant particles inside water, and they just start losing their supports from the surrounding soil particles. So in this case, we call this phenomenon boiling, or in a more technical term, we call it liquefaction. Eventually soil starts to boil or liquefy. That means that it starts to act as just a liquid. And the main reason is we are having zero effective stress in soil. So this is the classic definition of the liquefaction. The pore water pressure increases, the effective stress decreases, getting zero. The soil particle are losing supports and they start liquefy. And in that case, if there is any structure above the soil, because the soil particle is going to lose their support and the stresses between the particles will get zero, therefore the structure, the superstructure also will lose its support, and then it starts sinking or flipping, and we got the catastrophic failure over there. So this is a classic definition of the liquefaction. So we have two notes here that is important to mention. And the first note is we are saying that in theory the effective stress gets zero and then the soil gets liquefied, but that's a necessary condition in the actual field. So in the actual field, the effective stress does not necessarily have to be zero for a soil to liquefy. So a minor value of the effective stress, a reduced value of effective stress still can be a sign of liquefaction or a sign that the soil is very close to a liquefaction state. So therefore, not an absolute zero is necessary, but even just a decrease of the effective stress might cause soil to liquefy. So this is an important note here. The second note that we want to mention is that basically the cyclic shear that is applied to the soil is not the direct reason or the direct component that causes the increase of the pore water pressure. So in this example that I was talking here, I was saying that the shear stress is applying to the soil and therefore the pore water pressure increases. However, we are missing a portion of that. So this is actually what will happen in the case. So what we are missing here as a component is the reduction of porosity. So that is actually the main reason that liquefaction is happening in soil. So therefore, the actual step that causes liquefaction is going to be the cyclic compaction of soil. So therefore, we are applying a cyclic load on the soil, and that cyclic load causes the reduction of porosity. It causes the reduction of porosity, and then the reduction of porosity causes the imprisoning of the water inside the soil particle, and then that causes the increase of pore water pressure, and then eventually, as we mentioned here, this causes the decrease in the effective stress. So as we see, the basic liquefaction model that is going to be implemented in FLAC is going to be also related to the porosity change and the void change inside the soil particle. And that is actually what we wanted to discuss here, so we know what would be the procedure for the formulation development. So that being said, once we got a quick introduction with regard to the liquefaction phenomenon and how the change of the cyclic shear stress results in the change of the porosity, and then that results eventually in the increase of pore water pressure and then decrease of shear effective stress. And now we are going to discuss with regard to the liquefaction modeling in FLAC, and we are going to talk about a constitutive model in FLAC that is used for the liquefaction, which is called the FIN model. And we are going to discuss this model based on the concept that we just talked about that here.